Okay, so before we stop, we make analog of, we make the relation between left invariant vector field and right invariant vector field relates to the angular momentum operator. We make this relation more precise, and we see that the right invariant vector field is angular momentum for the left part of the left factor of the representation space, and the left invariant vector field is the angular momentum operator for the right part of this tensor product. And both left and right, they are representation space of SU2, but if you tensor them, you get the state of loop quantum gravity, which is a function on SU2. So you see this is the reason why we get both Vj and Vj star is because we are talking about the function on SU2. Pi j is a function on SU2, but Vj is the representation of SU2, and Vj star is also the dual vector. It's the dual vector space of the representation of SU2. Okay, so of course SU2 can represent functions on SU2, but it's not an irreducible representation. So here Vj and Vj star, they are irreducible representations. So, but when you make a tensor product of two irreducible representations, you actually get the Hilbert space of functions on SU2. So better clarify these relations. And so here you get minus R square operator equals to actually angular momentum operator. So J square operator acting on Vj, the first factor, and so L square minus it's proportional to J square acting on J star. J star. Okay, and well, both of them has eigenvalue J and J plus 1. Okay, so I think these should clarify why you find right invariant vector field and left invariant vector field are just the same as angular momentum operators. So they are really the same. Okay, so any question about this?
I have a question. Yeah, and we know that in the standard quantum mechanics, the discrete representation for the bound states. So the representation for the area operator also discrete. So that it means that we need to do the quantization on a complex space.
Well, it relates. Well, even if you consider infinite dimensional Hilbert spaces, then the discreteness relates to the bound state, or not relates to the discrete spectrum relates to the bound state.
Yeah.
But here, well, your Hilbert space is just finite dimensional.
Oh, okay.
It's finite dimensional. Well, okay. Probably what you mean for the Hilbert space on the group. Well, for the Hilbert space on the group, it is indeed infinite dimensional, but you can view this is indeed a bound state because there's no infinity. Well, the group is compact. You can view it really. In case of consider Hilbert space on SU2, it is an infinite dimensional Hilbert space, and your wave function is equivalent to a bound state because every state is a bound state. SU2 is a compact group. There's no infinite. There's no infinity. There's no boundary. So every wave function is a bound state.
Okay.
Yeah. So that's why you get a discrete spectrum on even on the Hilbert space. Even you have an infinite dimensional Hilbert space. But suppose just the quantum mechanics, right? Just you consider quantum mechanics. Mm-hmm. Your angular momentum, if you fix J, right? If you fix J, then well, okay, probably you are asking the discreteness of J, right? Not discreteness of M.
Yeah.
This is J, yes. So you understand in in terms of SU2 function. And just like I explained, although function on SU2 is in the Hilbert space infinite dimensional, but all those states are kind of like bound state. It doesn't really contradict.
Okay.
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 All right. So, is there any other question?
I have a question.
Yeah.
About the right invariant vector. It's a derivative act on the pi, correct? And then you get a GK operator.
Yeah.
But I think there is another exponential e to the net I epsilon 1 GK.
E to the I. There's another e to. Oh, okay. So writing. If you look at the right invariant vector field definition, there's a epsilon 1.
It's equal to 0. Okay. Oh.
0. So if you look at the yeah, so you see. So it's so the right invariant vector field. You first make the translation and take the derivative, and then in the end you take epsilon equals to 0.
Okay, thanks.
So this is yeah. So this is not just the derivative operator. This is like derivative, and yeah, it is also a derivative operator at the point where you take this translation. Okay. So any other question? Okay. So otherwise we just continue a little bit about the volume operator, and then we stop. Okay, so let's talk about volume operator. Okay, so again, let's look at this is our space sigma, and we look at a some weird, well, arbitrary region. Again, I'm still drawing the two-dimensional analog, so we suppress one-dimensional. When we suppress one dimension, and we just consider a region, a three-dimensional region in our spatial slice. Dimension R is 3. So we are not talking about the surface. We consider a volume, a three-dimensional region, right? And now we are going to write down an expression for the volume in terms of holonomy and flux, in terms of flux especially. Okay, so how to do that? We are going to discretize the volume of R of this region. So again, we introduce the lattice. Okay. Now you can consider this volume is it's actually made by smaller volumes concentrated at each vertex. So you can distribute this volume at each vertex, and you can the discretization is that you consider a box at each vertex, yeah, and for all the vertex inside this volume, inside this region. Yeah, so this vertex also inside the region, so you consider the box. Okay, here it is also in, right? Okay, so now you can approximately write this volume to be a sum over all the vertices, where this vertex is included in the region R and V of V. Yeah, so this is the volume of that box at the vertex V. VV is volume concentrated at the vertex V. Were contributed by the vertex V. Okay, now we are going to write a discrete formula for this V of V. Now let's still come to the region. Well, come to arbitrary. Arbitrary region R, and we know the volume of this region R is D3x. Determinant Q equals to R D3x. Well, determinant Q is just the determinant of E. Determinant of EAI. Well, and then you can write more explicitly this determinant. So here the reason is that EAI equals to square root Q EAI. Okay. More precisely, there's absolute value because it relates to the E is left-handed or right-handed. So now you got absolute value 1/6. So BC okay. Right. So just write the determinant in terms of epsilon symbol. Again, so these epsilons are all epsilon symbols. They are not epsilon tensor. They are not tensor. Okay. All right. So now again we are going to consider these region. Well, consider as I said, this is the sum over V at V, and this V at V it is just V in case R it is box of V at V. This is just this box. At V. Well, this is using the picture to illustrate this box. Okay. Right, and you just then this volume of this box is just the same formula as above. The only difference is that you replace R by this box. Okay, so now what we are going to do is just to discretize these square root, this integral of the square root. So now I'm going to tell you the result. Yeah, and I will ask you to check the continuum limit of that. Indeed, go back to the continuous volume. So VV will be a square root of QV, absolute value of QV. So this QV equals to this beta 3. By the way, before write down the formula, I better clarify some notation. About the edges. So remember that for every vertex, every vertex is 6 valent, okay, because we are in the cubic lattice. Yeah, and in our previous notation for the edges, so we write this is V. We oriented the edge such that there are 3 edges outgoing and 3 edges are incoming. Okay? And then you get EI V. So this is E1 V, and this is E2 V. And this is E2 V, and this is E3 V. Well, but this is will be E3 V minus say 3 hat. Yeah, so this is a outgoing index from the vertex, which is before V in 3 direction. Yeah, so this is one way to labeling those edges. But it is more convenient, for example, when we talk about volume operator and later on talk about operators for the Hamiltonian constraint, it is more convenient to take a different labeling, different orientation, different assignment of the orientation. This is a vertex, and these are 6 edges. So we orient. So when we talk about the locus, when we talk about the locus at the vertex V, we are going to orient all the edges to be outgoing. So here we only consider outgoing edges. And by flipping the edge, we only need to flip the holonomy, replace all the holonomy by inverse. And also, I think there was a homework to check that there's a relation between flux operate. There's a relation between flux if you flip the orientation. Okay, so I'm also going to write down that in a moment. So here, when in this way of orient the edge, so here we are going to write this edge to be E V. So I'm going to put the vertex and all the orientation, all the information about orientation to be indices. So I will going to write this is V1 plus. And the edge here will be EV1 minus. And similarly, here this is EV3 plus, and this is E3 V3 minus, and this is E2 plus, E2 minus. Okay, so all these edges labeling in this system will be outgoing from the vertex V, and this is, it means plus means it's outgoing in plus direction, and minus means outgoing in the minus direction. And you can easily get the relation between these two different way of labeling. So here this EVI plus equals to EIB, and EVI minus equals to EI V minus I hat inverse. Huh? Okay, so this is the relation between two different kind of labeling. So now we are going to use this kind of orientation to write the expression for Q and the volume operator. Okay, so this Q is written as following. Okay, and then there are 3 factors of flux, but this flux is not a single flux. It is a average of the flux in both in positive direction and in negative direction. V1 plus minus PK EV1 minus, and similarly for E2 plus yeah. So I have to squeeze the space. Okay. Well, it is a bit dense, but well, if you define some variable called x, v, let me see, v j I to be just as the numerator pj v I plus minus pj v I minus, okay, and this qv is just with just 3 epsilon ijk and 4 pi j1 v x2 3k. Well, probably I missed the ijk. Okay, so this is here is still Einstein summation between I, j, and k. Okay, so this is the expression for q, and the discrete volume at vertex v is just the square root absolute value of q. All right. Now, so the claim is that any region R can be written as sum over V square root absolute value QV. QV is expressed above. Okay. So you well, up to higher order in mu. So the volume is of order mu cube because this is a volume, and then the higher order is mu to the power 4. And now it's your homework to check this. So it's your homework to take the continuum limit of square root of q, and to show that it indeed converges to the volume. So firstly, okay, probably this is something you didn't really prove before. So firstly, you need to, you also prove the continuum limit of square root of q converges to the volume. You need to first prove the relation of p. If you reverse the edge. So prove this. Prove pj evi minus equals to 1/2 trace tau I column e v minus I hat. So this proof also helps you to familiar with this labeling system. V minus I hat. So this V minus I hat, it means V minus I means one vertex before V in the I direction. Okay. Now the space, and then the H minus I hat. Okay. Well, what is V minus I hat? So this is this vertex. This vertex, this is V. This is V minus 3 hat. And this vertex is negative direction. So this vertex is V minus 1 hat. So we label edges in this way, vertices in this way. Okay, so firstly, you need to prove this relation. So if you reverse, so so this means that you can see that this is positive direction from v minus I hat. So okay, I found here I oriented wrong. Anyway, so this is EV1 minus, right, in this notation. And however, if you reverse it, if you reverse this edge, it will be EV minus 1 hat 1 plus, right? So you see that the left hand side is EVI minus, the right hand side is PV minus I hat I plus. So this edge is just the inverse of this edge. So this means that P has some certain transformation if you reverse the edge. The flux also transforms if you reverse edge. We know that holonomy transforms simply. If you reverse edge, holonomy just becomes holonomy inverse. But flux also transforms. The transformation is a little bit complicated, but this is like a sandwich. It's like a joint transformation, a joint action. Okay, so first you need to prove that. This is you just use the definition of the flux, and secondly you have to use this formula to prove the continuum limit of the volume. Prove of the volume, namely at the vertex V is a mu cube determinant VI used before. And well, all these proof can be done in Mathematica. Actually, all these proof can be worked using Mathematica. So you can design your Mathematica code to do this computation, or it is also not hard at all to compute by hand. Well, and to prove that, it is very easy because you can use this hint, because you can first study the continuum limit of the flux. So the hint is that P J E I S. S is either +1 or -1. Plus -1. And I equals 1, 2, 3 direction. And it actually equals to beta mu square times S, and then EJI. Right. And this EJI, it is just the coordinate index if you adapt the coordinate to the lattice. So the flux, well, the first leading order is mu square, and higher order is mu cube. And here this I means that you consider this is your lattice. So this is x1, x2, x3. So this means xi. So this I is just the coordinate index adapt to the lattice. Okay. So this is your homework to check it out. So here, I think there was a homework, right? There was a homework about proving the continuum limit of the flux. You need to use that formula. So if not, if you haven't done that, you have to prove first. Prove first this relation. Okay, so now we have written the volume in terms of flux operator. So then the quantization is straightforward. The volume operator of R equals to V hat, and here V hat equals to square root absolute value of Q hat operator. But in quantum mechanics, how to take absolute value and square root? It is actually the following. So these actually equals to, you first need to take the square of the operator and then take the 1/4 power. Yeah, and firstly you take the square of the Q operator, and then how to take 1/4 is that you first need to diagonalize this operator and then take the eigenvalue to the 1/4. This is the way in quantum mechanics to take the square root of the operator, or 1/4 of the operator. Yeah, and that's the complication of the volume operator. Okay, and then this QV hat, it's just you replace the previous P by P hat. Okay. Well, I'm just going to use X. Okay. For hat I1 P. And this X I J. P J. Okay, so this is the volume operator. This is the operator Q, and then you plug Q into, and you take the square of the Q and take the power 1/4. And you get the volume operator. All right, so let me stop here. So it's better stop. Yeah. So we continue to talk about volume operator next time. So any question?
Hi, is this next lecture going to be Wednesday and Fridays?
Yes, yes.
Okay.
Next lecture will be on Wednesday, and then it's the same as before, Wednesday and Friday. 11,
Okay, good.
11 a.m.
All right, thanks.
Okay, so any other question? Well, if not, then see you next time.
Thank you.
Thank you.
Thank you. See you.
Thank you. See you.